Okay, so another fantastic session, which I'm quite excited about, plate heat exchangers and substations. So we've got a talk on standardizing plate heat exchangers and control approaches at substations. And just as some background to this, we select this as a topic as it is something we've seen as an issue in the wild, where we've seen big fluctuation in temperatures. So that's why we selected it and got it looked at. So as an introduction, we've got three speakers today. So we've got Dan Staunton, who's a senior engineer at FairHeat, Lucy Sherburn, who's a graduate engineer at FairHeat, and then Soulla, Paphitis, who's software solutions manager from Danfoss. Thanks all for coming on.
Thanks for having me.
Thank you, Gareth.
Thanks.
So,
yeah, okay, I can't quite get.
That's okay. Just tell me, and I'll
go with you do it.
So, as an industry, we're seeing an increasing need for plate heat exchangers. Building heights are increasing, leading to higher pressures on networks. Plate heat exchangers reduce those pressures, minimising risks to residents and protecting plant equipment. As building heights generally increasing over the last 5 to 10 years, we're seeing, and continue to do so, we're seeing an increased need for plate heat exchangers. Next slide. Historically, though, outlet temperature stability from plate heat exchangers has been poor. So the data on the right-hand side here shows the secondary temperature flow temperature off a plate heat exchanger taken just a couple of weeks ago from the site. During periods of low demand, so before around 5 o'clock in the morning, we're getting really quite unstable temperatures. The target outlet is 70 degrees, but it's varying between 75 and 60 degrees. As demand starts to increase, sort of past 6 o'clock onwards, we start to see slightly more stable operation, but still fluctuating between 75 and 65 degrees. Historically, this has had a relatively limited impact on residents. We've designed with relatively large approach temperatures between secondary flow temperatures and HIU outlet temperatures. So the scheme that this was taken from, whilst the plate was delivering at 70 degrees, the HIU was only delivering 55 degrees to residents. The plate could therefore vary around 10-15 degrees from set point without any impact on residents. Next slide. However, the tolerance for poor control and poor stability is reducing. We're moving to heat pump led heat networks. The impact on heat pump temperature and needing on efficiency, we're needing to drop temperatures. And whereas traditionally we would have had a 10 to 15 degree approach temperature from the secondary flow onto the HIUs, we're now looking more towards 5 to 10 degrees to retain efficiency on the heat pump. If we overlay, like we have done on the right-hand side here, the current levels of stability that we see, I should say this is a fairly common level of stability that we haven't picked out a particularly poor plate heat exchanger. You'll see that if we're trying to maintain a 5 degree approach temperature, we can't do that. So our current approach, our current designs, our current controls don't provide adequate stability for us to maintain comfort, domestic hot water and space heating continuously. Next slide. There are a couple of root causes for this. We generally see peak load still being oversized and the equipment being oversized because of that. Relatively limited consideration being given to part load and controls being poorly optimized. There also isn't really a standard approach that's being coalesced around as an industry. We had a quick look at the last couple of years worth of designs that have used plate heat exchangers, so from other consultants and clients. Around 50% used a duty standby approach, and 20% used a duty single plate approach, another 20% used the duty assist approach, and 10% of just other design. There's no clear standard that's being used, and that's preventing lessons learned being taken forward into the commissioning and specification of plate heat exchangers of control valves moving forward. And that was the purpose of Lucy's project.
Yeah, thanks, Dan. Yeah, as both Dan and Gareth have mentioned, this topic was given to me as a graduate project where I was trying to solve some of those issues that Dan had discussed with the aim of identifying an optimal approach. The model I developed investigated a number of different things. What I'm going to talk to you today about are brazed versus gasketed plate heat exchangers, sizing and selection of your plate heat exchanger, look a bit at load data, and also look at the cost of different options. Some of those options we looked at included different size plate heat exchangers, so going at one size at 100% and smaller plates. Also looking at different plate heat exchanger arrangements, so the duty standby or duty assist as well. The model used a 3-degree approach temperature across the plate heat exchanger. This was used to represent a low temperature scheme or heat pump led scheme. And I also used load data from a theoretical hourly load model, which was developed by FairHeat. This load model had 4 different scheme sizes, so going from 100 units to 1,000 units. So scheme size was also kind of investigated within this, but for the purposes of this presentation, I'm just going to look at the 250 unit size scheme. Next slide, please. So initially, I investigated brazed and gasketed plate heat exchangers. They're the 2 types we typically see in this industry. And I looked to compare their flow regime across the yearly load profile. So just going back to the theory a little bit, your ability to transfer heat effectively depends on the turbulence of the medium. So high turbulence is really desirable. Laminar flow, which is kind of at the opposite end, where you have low flow rates through your plate heat exchanger, gives poor performance. Your velocities are reduced. This can result in scaling and fouling on your plate heat exchanger. Can also increase the pressure drop across your unit. So this has a knock-on effect in terms of maintenance, lifespan, and your ability to transfer heat effectively. So we want as much turbulent flow as possible. So using the hourly load model at each load point within that, I was able to tell whether the plate heat exchanger selected was operating at turbulent, laminar, or transitional flow. And transitional flow is just the bit between the two there. The graphs compared different size plates for both brazed and gasketed solutions. And you can see kind of the breakdown of those different flow regimes across the year. I think it's pretty clear to see that brazed plate heat exchangers provided the highest amount of turbulent flow in comparison to gasketed plate heat exchangers. Next slide, please, Gareth. So then looking more into brazed plate heat exchangers, I compared the flow regime of different scenarios. So as you can see on the graph here, we had one plate sized at 100% of peak load, so your duty scenario. We had the same again, but with a spare plate located in the plant room. This was kind of looking at the cost of that, really. We then had duty standby. We then looked at duty assist approaches. So 2 plate size at 60%, 2 plate size at 50%. We've kind of seen these before in industry. And then we also thought to look at using almost like a jockey plate. So having a plate sized at sort of 20, 30 or 40%, and then having a larger size plate as well. So what can we see from the flow regime with this? We can see that duty plates and plate sizes at 100% give the least amount of turbulent flow and the largest amount of laminar flow. So should probably be avoided when going forward. Next slide, please. So the symmetrical duty assist plate heat exchangers, they provided an improved performance. So the 2 plate sized at 60% or 2 plate sized at 50%, the laminar flow amount decreased and the amount of turbulent flow increased as well. And next slide, please. We see that the asymmetrical duty assist plate heat exchangers, so those that have the jockey plate, provided the highest amount of turbulent flow and really limited the amounts of laminar flow. So if we take a look at load data, yeah, that one, perfect. We can kind of see why this is the case. This is operational load data from a site across the year of 2020. The design peak load can be seen by the orange line at the top. Then you can see the power across the scheme. We can see that actually for large portions of the year, you're operating at quite low loads. and you are getting close to peak load during winter, but you're kind of not necessarily hitting that. So takeaway from this is that your plates really need to be sized to operate efficiently over a range of loads. And if you're having a plate that is sized at peak load and actually you're only operating at 10, 20% of that, you're going to start seeing that laminar flow and have that reduced amount of turbulent flow. Next slide, please. We also looked at the proportion of year spent above a percentage of peak load. So you can see with the above 20%, there was 55% of the year spent above 20% of peak load, but that also shows 45% of the year was spent below that. So large portions spent again at low load. But what's interesting about this is actually when you have a plate size that either like 50% or 60%, there's not actually a significant there's a very, very little amount of time spent above that. So actually using those size plates almost provides you close to full redundancy. Next slide, please. I then looked at cost comparison. So as you might expect, the duty standby provided the most expensive option, and the duty assist options are kind of relatively similar in price to each other. There wasn't one that was significantly more or significantly less expensive. This was for the brazed plate heat exchanger with a single pick valve. And next slide, please. And just taking it back to comparing gasketed and brazed solutions, these are the different sizes of plates that were used in the model. For those plates that are at lower size, brazed was cheaper, but as the plates got bigger, they were actually really relatively similar in price as well. Next slide. So what can we conclude from this? Well, it appears that brazed plate heat exchangers give better flow performance overall, but when you have larger schemes, consideration may want to be given for gasketed plate heat exchangers, just because gasketed can be assembled in a plant room or disassembled and reassembled pretty easily. So if you've got a really heavy unit and your access isn't great, gasketed might be an easier solution because you avoid the need to lift heavy things and can get through access a bit easier. Plate heat exchanger sizing, I think it was kind of clear that using a plate sized at 100% is probably not the way to go. So that leaves the duty assist options, but which one? Well, theoretically, using a jockey plate appeared to be the best approach in terms of flow performance, but we kind of haven't really seen this approach used on site or have experience with it. So we need to kind of investigate and determine feasibility of using these asymmetrical plates. So in the meantime, using a 2 plate sized at 50% appears to be the best approach. So the duty assist at 250. This provided you with pretty low levels of laminar flow. It was ever so slightly the cheapest duty assist option. The load data suggests it will provide near enough full redundancy, and we have established control methods for symmetrical duty assist plate heat exchangers. Should note that this is quite high level, and there are many project specifics that you should consider when choosing your plate sizes and what type of plate. And control valve selection will play a major point in getting those stable temperatures, which Dan was talking about at the start. So that kind of is still a major consideration. So so on that, I'm going to pass over to Soulla from Danfoss. She's going to discuss the control valve side of things and hopefully provide some solutions to the issues we're seeing.
Thanks so much, Lucy. And it was great to actually see the difference between the heat exchangers there and the work that you've put in. So thanks for that. So we could just go on to the next slide, please. Yeah. So just sort of going back over a bit of the theory here, I guess. So let's see how we can achieve this perfect flow in a substation. So the equation that you've got on the left there requires us to control the kV and differential pressure in order to achieve a perfect flow. So without any valves in the substation, you're not looking at controlling anything at all. So the behaviour of the substation would be completely unpredictable. As we install a motorised control valve, we gain the ability to control the kV, which is the valve opening part of the equation there. Since the system is dynamic and the differential pressure is changing all of the time, this will in most cases give you a very poor control. And you can see that by the changing temperature in the graph at the top where the domestic hot water is coming from. With upgrading the substation with a differential pressure controller, we can achieve full authority over the flow control. And in most cases, we can achieve a perfect control. But there are still cases, however, where this is not possible. For instance, where you're looking at oversized valves or uncommissioned controllers. However, in those cases, the results with the motorized control valve will still be better than having no control on there at all. So in most recent years, we've looked at using PICV controls, which basically combine the motorized control valve and the differential pressure controller into one complete unit. Next slide, please. So with the use of our latest technology, which is the Vertus PICV, and autonomously controlled intelligent actuator, which is the ISET, you have the ability to change the differential pressure over the motorized control valve. And this ensures flow stability for high and low flows, and with the added benefit of having a more compact design and added setting indicator. The split characteristics of the Vertus PICV offers improved control and higher accuracy. The intelligent differential pressure adjustment ISET actuator improves network efficiency by offering continuous auto commissioning and providing pump cost optimization, and can offer predictive maintenance when it's being monitored. As you can see from the graph here, and this is a real life case study that we've been involved in, you can see the benefits of installing this technology. So you can see on the left-hand side that there are big flow and temperature oscillations, and these are measured on the secondary network, especially during the low demand periods. You can see in the middle proportion there where ISET has started to kick in, and it's starting to lower the differential pressure control and oscillations. It also shows on this right-hand part of the graph where ISET is fully functioning. It's learned how the demand flows from the heat exchanger and the system itself, and it's starting to provide a much better comfort condition for the end users. So this is the part that's being delivered into your tertiary side of the system. So ISET function monitors flow control signals from electronic controller where it detects a signal and is oscillating. And this is enabling it to stabilize the temperature control. It starts intelligently lowering the differential pressure on the flow control valve, and consequently that forces it into a higher opening and out of non-authority range. If you can move on to the next slide, please. So, you know, using the correct valves is extremely important, and understanding how they affect your system is also a really relative and relevant point to consider. But also with the current situation that we all find ourselves in, I believe that data-driven approaches and being able to remotely connect to your heat source to understand what's happening is an extremely important factor. So Danfoss Lean Heat Monitor is, at its base, a monitoring and control solution, allowing you to have control over the heat transfer demand as well as the network and the production. So with the development of this solution, we looked at 4 main goals. So being open, connected and transparent, meaning that the software can connect with any device using standard communications. It offers easy integration and business intelligence and optimization solutions. In a simple term, it's plug and play. We looked at modern web-based cloud solution, which is constantly and always updated. So with the latest version automatically available to you, you can access it from anywhere on your mobile, desktop or an iPad. And it's offering you state-of-the-art security mechanisms for a safe and secure communication and data storage. This solution has been customized for district energy systems with easy integration on new devices. So as your network grows, you can add more devices to your network. The controllers are automatically commissioned, and the solution can improve your network control and management with actionable information, insights, and seeing the improvement of your work efficiency of the actual network itself. And also by providing this kind of solution and being able to use a data-driven approach, it offers a reduction in your investment and maintenance costs. The software as a service will help lower your total cost of ownership and improve your return of investment by unlocking your resources to focus on your primary business. We can move on to the next slide, please. So with this intuitive software, you can access a wide range of functionalities, and it's so important when you're looking at the controllability of your product that you've got on site. So not only is selecting the right heat exchanger and selecting the right valve important, but actually understanding how they're working and how your system is operating. With this software, you're able to get a number of different functionalities, including maps, flow diagrams, real life data, understanding what your flow and return temperatures are and what you're actually delivering from your heating circuits and your domestic hot water. You're able to download the files as CV files, and you're also able to create charts and graphs so that you can actually prove and show how your system is operating. One of the most critical things, and this is something I think that Lucy and Dan have looked quite a bit into, is that at the point of when you commission a heat exchanger or a substation, you're only ever commissioning to the standards of that particular day. And this is where obviously seasonal commissioning becomes far more important. If you're only able to commission on a specific day and it's 5 degrees outside, that doesn't give you a true indication as to how your system will operate when it's -2 or it's 25 degrees. Next slide, please. So just to show you how, looking at weather compensation when you're looking at your substation and heat exchanger is really, really important. And it's something that should be taken into consideration when you're looking at how you're controlling your substation. So as you can see on this graph, and it is quite small, so apologies if you can't see it properly, but you've got on this chart, the green line is showing you the flow temperature from the secondary flow, and the brown line is showing you the heat meter power in instant kilowatt. So the weather compensator is saying that if the outside temperature drops, there is an increase in the kilowatt demand and the flow temperature. And when the outside temperature rises, there is less demand for power and temperature. So what this is showing is that without weather compensation, you would have a fixed flow temperature, which in 99% of the cases would be too much. By using weather compensation functionality, you start to create energy and money savings through your equipment. A minimum temperature can be set during weather compensation to ensure that your domestic hot water demand is achievable. And I know that the domestic hot water side of a network is so important, and in the previous presentations you would have heard as to why that is. And while this appears, weather compensation appears to be a very low level control, there are very few systems that I see in the field that actually use this functionality of control. By using a data-driven approach and a smart software, like Lean Heat Monitor, this would automatically be a function rather than something that needs to be manually set. Thank you.
Great, thanks though all. We've got a few questions that have come in. If I just come into those. First question, actually I'll jump to the second one now. Approach temperature is a question from Oliver Butcher. Approach temperature is a new term to me. Could you confirm what this means in the system?
Yeah, so approach temperature is the difference between the temperature on your inlet on one side of your plate heat exchanger and the outlet on the other side of your plate heat exchanger. So your primary flow and your secondary flow essentially is the difference there.
So just to note that the difference in your approach across the plate will change the size of your plate as well.
Yeah.
So it may change the size of the frame, the height, the weight, the width, and the amount of plates that are involved. So I know that you used the 3-degree approach in your study, but primarily and more often on a heating circuit, we would see around 5 degrees, and sometimes on a chilled system, you'd see between 1 to 2 degrees, but a 3-degree approach is where a lot of designs are going to at the moment.
Yeah, and a 3-degree approach is just purely as we go to lower temperature schemes. Obviously, that difference between what's coming out of our heat generation equipment and the temperature that's at the final point in your hot water, that is starting to kind of reduce. And yeah, it's proving that your plates need to be bigger and lots of other things as well.
Yeah.
Another question, what further consideration should be made when specifying the type of plate heat exchanger? And I think this comes back to what you were looking at before, Lucy, in terms of branded and gasketed.
Yeah, so I think I kind of touched on this earlier. gasketed plates can be assembled and disassembled, whereas brazed is a unit that can't be opened up and put back together. So yeah, like you said, if you have a large scheme and you have really big units, it might be easier to have a gasketed plate because you can assemble that in your plant room. But other things to think about, what I found was when I compared it, gasketed tended to weigh more when it was put together, needed a bit more floor space. So that might be a consideration of how much floor space you need. Again, with the reducing approach temperature, this tends to mean that you need a 2-pass solution in your plate heat exchanger. So instead of having both your connections on one side, you have them on both sides. So that might be something you need to consider, as whether that's going to increase your floor space again. Gasketed can be a bit more flexible in terms of adding and removing plates. If you were increasing the size of your scheme at a later date, that can be easily done. Again, with maintenance, I looked into what the differences in maintenance between the two. And what I kind of got back from industry was, well, a well-maintained system, there should be little maintenance, but we all kind of know that systems aren't really well maintained. So, but as we saw with gasketed, they weren't very efficient in terms of their turbulent flow. So if you have more laminar flow, it's likely that your plates are going to get scaling and fouling. So that might mean your gasketed plates are going to be needed to clean more often than, say, if you had a brazed solution. So that might increase your maintenance costs. And again, with gasketed, because your plates are sealed by gaskets, they often need replacement during lifespan. So that's another additional thing you might want to consider, is like the cost of replacing your gaskets at some point during the lifespan of the plate. Also, yeah, that needs to be considered, whereas you don't really have that with the brazed solution. So yeah, there's kind of various project specifics that you might want to think about when it comes to it.
They're really great points, Lucy. And I would always say that there should be as well on the rating of the kilowatt rating of a plate, there should also be like a level of where you moved from a brazed plate onto a gasketed plate, just surely because of the size and the weight of the units themselves. But you know, like with a brazed plate, if you're doing sort of 400 kilowatt, the performance of the plate is better as a brazed plate. And actually, when you look at the maintenance costs and the regimes for a 400 kilowatt gasket plate and what you have to do in the future, it works out that the brazed plate is more cost effective.
I've got a question coming back. So Soulla mentioned before the issue around, you know, obviously oversizing isn't only on plates, it can also be on valves, and that can have a really big impact. You looked at modeling different sizes of plates, Lucy. Did you also look at the impact of modeling, what the impact might be on valves? Yeah,
I kind of looked into that. It proved to be a bit difficult in terms of manufacturers say they can control down to 1% of nominal flow. So if that's the case, that's brilliant. The old flow should be able to be controlled well, but often we don't necessarily see that. And it's kind of determining whether that's down to, is that 1% accurate or not? There's actually, when you're below 20% or 40% of flow, you might see the valve punting or oscillation. Or is it maybe down to like the control logic and tuning and commissioning of the valve as well? So that's kind of where I got to in terms of trying to figure out what is actually causing that, and kind of yet to be fully investigated.
So I'm going to be challenging here, Soulla. Can we believe, yes. Can we believe the 1% figure? Because I mean, just from anecdotally on site, looking at empirical evidence, that would appear to be the case. Yeah,
I mean, there are a number of different factors with how a system performs. Selecting the right plate, selecting the right valves. Every manufacturer of a pressure independent control valve or motorized control valve, whatever it is, should be able to give you and supply to you as industry testing certs that show how the performance of the valve will work. You can control down to 1%, and most manufacturers out there will tell you you can. It doesn't explain the amount of oscillation that you may get through the system. Hence the reason why using an autonomous controlled product would help with that, because it takes a learning from the system and it starts to control based on the demand. So using a technology that can take out that oscillation and that variant in there is really, really important when you're looking at moving into these low temperature systems where you'll start to get different temperature approaches and you're oscillating and your system is fighting. The other problem that we also see, and I know that Lucy and I'd spoken about it previously before, is where there's not, you know, where you've got buildings that are being handed over and you've only got 30% residency and the system's been designed to 100% residency. You know, it's switched on because 30% of there's occupancy in there. The system's trying to deliver and it's been set and commissioned to deliver at 100% load, and you don't need that. You're using excess energy, and this is where you're getting higher pumping loads, and your valves in the system aren't able to cope with that, and that's where you get these oscillations. So using data-driven approaches and being able to commission, I guess, on a daily basis as to what your demands are really important to running an efficient system.
Okay, we've got one final question and we've only got about a minute and a half, so quick answers on this one. Do you have any comments on rule of thumb sizing with respect to pressure drop limits set on plate heat exchangers? E.g., a very low pressure drop limit may be set, which will lead to a high level of oversurfacing on the plate.
So yeah, I'm not necessarily a heat exchanger specialist, but what I came to find when I was selecting plates was obviously at these really low small approach temperatures, you needed a higher pressure drop to not to be able to have to transfer heat at that approach temperature. It was kind of impossible to have a low pressure drop and a small approach temperature to be able to provide a solution. I'm not too sure on this whole oversurfacing and that sort of technical detail at the moment.
Yeah, there are quite a lot of factors that you do need to consider when you're looking at the pressure across the plate as well. So there are a lot of designs that come out with like 30 kPa across the plate, which really changes the amount of surface that you have in order to get the heat transfer, like Lucy was saying. 50 kPa is generally quite a nice figure. Around that point, you can get a plate that will be efficient and that will work efficiently. So we try generally when we're selecting plates to select around the 50 kPa mark. You know, we can select at 30, we can select at 20. And again, it will also depend on the actual system itself and the pressure, the pump pressure through the system. If you've got a 250 kPa pump right next to the plate, then you need to take that into consideration when you're making the selection.
Yeah, I think it's another kind of, it's all kind of project specific in a sense of what do you want through your plate and whether that's worked. In terms of the model that I did, we used a 50 kPa pressure drop limit across the plate.
That's all we've got time for. Lucy, Soulla, and Dan, unfortunately, has internet crashed, sign of the times. Thanks a lot for coming on. Much appreciated.